And this is what we are going to do. First, we have to select the spaces and the construction details. Well, the construction details, I will provide you with the construction details because I have a detail from this building. And well, the third stage of the project will be to analyze a construction detail with therm. The same thing we did with on the first midterm, yeah. But you will end up doing this with therm, probably the roof to wall connection. We have the detail of the roof, we have the detail of the wall, and then you have to connect these two details, and we have to analyze this with therm. Today we're going to explain how to select the spaces. Okay, so if you open this element, you open this this file. Let's open one of the levels. So you see that there are spaces here, but I don't like it. Why? Okay, so let's select this section here. So if we open section 1, we can see that spaces are not well defined because they are not getting up to the roof. And remember that if we analyze heating and cooling loads, and we have the spaces here, but if we go to details, there are a lot of warnings because none of the spaces are well defined. If we find a file like this, we can select every space, we can try to fix it, we can say, okay, the limit offset is 0, the upper limit should be level 3, and now that space will be okay. If we go back to the heating and cooling loads and we see the details and default, one of the spaces should be, okay, so this space is fixed. But it's the space 201. So another thing we have to do is to name the spaces accordingly, because otherwise it's a mess. So what are we doing? So what shall we do now? Instead of going space by space, well, we can always select like a window like this. We can filter. We can select only spaces. And we can adjust. Okay, so now all these spaces are well, and there will be more spaces without warnings. You have this one, that one. The problem is that we have to do this with every single section. So we will go here. Yes, so here we have only 2 spaces, this one and that one. Then on this section, there will be a lot of spaces, and we have to select all these, filter, we isolate spaces, apply. We find that none of them go up to level 3. And now if we analyze the heating and cooling loads, there will be more spaces fixed. Okay, so all of them are fixed. Yeah, we can do that, but I don't know. I think it's better if we select all the spaces. Look at this, we cannot. Yeah, if we use a 3D view, we don't select the spaces. So we have to do this either in section or in plan. So we cannot select all the spaces in the 3D view. We have to go to the plan, and now we select everything. We filter spaces. We have selected all the spaces of this plan. We can always go from level 1 to level 2 because we are on the first floor. And now we can go to heating and cooling loads. Okay, so now we are fixing a lot of them. But all the spaces on the second floor are still with a warning. Okay, so there are different things. If we go to level 2 now, I select everything. I filter spaces, and the upper limit is level 3. The offset would be 0. And now most of the spaces would be without warnings. Yep, all of them are without warnings. Okay, so that's an option. You select the space in the plan. But what are we going to do today? I want to work only with a part of the building, with this zone of the building. Here we have classrooms, and here we have all the offices. So we are going to analyze in this project, we're going to analyze only the probably this one. This is level 2, so this is the studio. This is the create space. We are not analyzing this. There is no point in analyzing the space like that. This is the classroom, that classroom. I don't know what the name of that classroom, what is the name of that? 2010 or 210 or?
I think it's a little studio. The big studio is 201. I think that's 203.
203. Yeah, this is 203. And this is the GAT lab. This is 207.
Yeah, so.
Yeah, so we are going to analyze the studio. We are going to analyze this one. It's 203. We're going to analyze the GAT lab. And we can analyze the lobby. Okay. In this case, well, we are simplifying the building, the lobby. You know that there's an opening here. So in theory, the second and the first floor belong to the same space. But to make it simple, we don't have this. Okay, so we have space for the lobby on level 2, and we have another different space for that lobby. Okay, there is not a space for this lobby, so we can always I think there is a space filter. Okay, so we have this that space on level 1. I think there should be like doors somewhere to make it a little smaller. But anyway, so this can be considered like a huge space, is the lobby and the corridors. Okay, so we are going to analyze only the second floor, and we're going to analyze the architecture realm, which is the studio, the grid space, 203, 207, and the lobby. We're not analyzing all these tiny elements here. Well, so there are two ways to address this, because now what is the name of that space? It's number 201. Is this the studio 201? I think so. But I would say studio 201. What is the name of this? Is 200A. I don't know. I would name it the grid space. And what is this? This is the lobby of the second floor. And this is 203. This is the classroom. 203. And this is the 207, but this is the CAD lab. Okay, so now when we are selecting the spaces, we know what we are analyzing. And if we are analyzing the heating and cooling loads, in these details, we can find, yeah, the CAD lab, the classroom, the grid space, and the lobby, and the studio. Okay, so we are analyzing only 1, 2, 3, 4, 5 spaces. When we are working with this heating and cooling loads analysis, we can calculate it takes time because there are a lot of spaces. Okay, in this building summary, Okay, we have all these spaces. We're interested only in this one. So we can always click here. And here, this is the grid space. And here we have the area, the volume. Okay, so we are analyzing this. Here we have different wall, window. These are the lows that we have usually, as it was expected. The windows in this grid space is something important, especially for cooling, for heating. Okay, so and if we want to analyze a different space, we can work with the cat lab. Okay, so here we analyze the cat lab. Windows are always the most important component in terms of heating and cooling load, as it was expected. So that's an option. We can generate, but we have to fix the spaces. Or we can work with spaces from scratch, or we can, I think that's enough. If we select all the spaces in the plan, this building, it's easy because we have two different floors and we don't have double volumes. The only double volume that we have is the lobby, and we haven't considered this as a double volume. Okay? So you can select all the spaces and then you can adjust and then you check that there is no warnings on this detail analysis. So as long as we don't have any warnings here, I'm fine with this. And then make sure that the spaces that we are analyzing, they have a name, that it's not 201, 203. So it can be 207, 203, because this is the actual name, that name them cat lab, classroom, grid space, lobby, so that I can understand what we are doing. So this is the first thing we have to do here. We have to select the spaces, and well, you can always select the building, and then we can select the spaces that we are analyzing. If I filter only the spaces, this is not a part of the analysis. Okay, so you can print this plan, and when we are selecting the spaces, okay, and that it would be great if you can place here space studio one, grid space, whatever the name of it. Okay, so that would be great. But at least we have to analyze the building, and we have to convey the information of what space we're analyzing. By the way, we're not analyzing those tiny spaces here, so we have to remove this one and that one. Okay, so we'll do it again. There you go. So those are the spaces we are analyzing. We are not analyzing this. This is not a space because this is the staircase. So in the staircase, we don't have a heating or cooling system. So we don't define a space here. So there's another staircase here. So we don't define spaces here because usually we don't have heating systems in that kind of staircases. This is it. We're analyzing only the second floor, and we're analyzing all these. So that would be the first part. And then the construction details, I will upload construction details on this building. So you have to prepare a report working with those construction details. The second part, the Revit model, the structure for the PV array. Well, I told you that we have to analyze this location key, New Hampshire, angle 15. We're not supposed to do this yet. This is the area, 821. I don't mind. The area is up to you. It doesn't mean that you need to do this area. You can design this roof. it should be something similar to the building, but there is not a specific area that you need to abide with. So we don't have this one because that was just an example. And now the second part of this analysis is this 3D building. I'm going to delete this one, and I'm going to delete all the structure. Okay, I'm deleting it. Probably you should save this as another file. And now we have to work with a different option. So what is the PV potential of that roof? We agreed, or we showed, that the optimum angle is around 40 because the latitude of King is around 42, 43. So a good angle would be 40. The problem is that if we have an open rack like this with an angle of 40, it will be extremely high, and we can't afford that. So the other option, and I'm sure that they will be considering these two options, and finally they made a decision on the other one, but I'm sure that they considered the option of, let me work, where is the section? Okay, so I'm going to use this section, and I'm going to use this section here. And I'm going to start on grid 6. Okay, this is the roof. And now we can create a roof by extrusion. I'm going to select grid 6 as the first one. And I'm going to do this. What is the size of this panel? Well, you have to select the same panel that we are actually analyzing. I think it was 1 meter, so that would be 6 inches, 6 feet, 6 feet, sorry. Okay, 6 feet is a regular dimension for a panel. We have to create a thin roof, so I have this 2-inch roof, so that's fine. And I create OK, I click OK, and this is the first row. It's here. Okay. Obviously, we have to adjust the size of the panel, and we cannot place the panel here. So we have to go to the section and wireframe. Yes, so I think this is the limit. So we have to move this in this direction. Okay, that's an option. And then we need to, how many rows can we? So now I can copy multiple, and yeah, make sure that the distance is enough. I don't know how many rows we can have. Okay. So imagine that we are analyzing this option. That's another, yeah, we have the option 1 with this roof, and we have option 2 with that roof. What do we have to do now? We have to analyze this. I have to check on the angle, because the angle, I don't. date, angular. Okay, the angle is 39, should be from 40 to 42, kind of. And now I want to analyze this from the PV potential point of view. Make sure that we are analyzing, we are comparing apples and apples, or pears and pears, or I don't know what the saying is. But here we are analyzing PV production, building energy offset. This is an annual PV analysis. You see that, or I explained to you how we can do this on a monthly basis, or in winter, or in summer. Here we are analyzing the annual PV energy. Okay, so make sure that we are comparing the same analysis. If it's a month, you can analyze this in the same month. If it's a season, winter or summer, or if it's a year, make sure that both analyses are the same year. When we are making that decision, usually we use the annual PV energy. So let's do this. Now we have to go to the sun settings. We have to select multi-day 1 year solar study. Okay. And now we have to go to analyze, solar, and we have to select solar energy annual PV. We have to select only this. Do not select all the roofs, or do not select the floor there. So we have to select only this. Finish. And now cumulative insulation PV energy in kilowatt hours. The units are important here. Okay, so we are working with the kilowatt hours as well. And the solar analysis, annual PV, the update. Okay. So this is the outcome. Okay, I think the distance is good because we don't have shade between these two rows. And now we can compare. So here we have 821 square meters. This is 560. So we have fewer square meters with this. What is the production? This is 131, and this is 179. Okay, more area, more production, but now it comes the economic analysis. So what can we do with this energy, and with how much this PV array cost? That would be much more economical. I wouldn't say cheap. So we don't have to pay so much money up front, because with this option we need to build the structure. With this option we don't need to build like this structure. And do we like this? Well, I think I like it. When you look at this building, the first thing that catches the eye is this PV array. With this, you wouldn't see the PV array, and probably that building would be less interesting. Well, I don't know. There are a lot of components that help us make a decision, that we are analyzing area and the PV yield, or the PV production. But now we can compare. Okay, we can compare this to that. So that would be the third. Well, this is the PV analysis. And now we have to compare the Revit and the PV watts output. And how can we do that? Well, now we need to give some information about the PV panel. So you remember that we have two different PV panels, the Chinese one and the other one. I'm going to use the Chinese. No, this is the Canadian. I'm going to use the Chinese one. Okay, this one is we have the standard test conditions, SCT. So this is what we are going to use. Again, if we are comparing two different panels, we have to compare either this or this. But okay, usually we are working with the standard test conditions just for comparing the performance of two PV panels. And this is 250. Okay, so now we need to provide information about the PV panel. We want to compare PV watts and the output. We need this PV panel. And if you remember, we explained how to do this last time. Okay, so we need to answer different questions. So this is the maximum power at STC. What is the maximum power at STC? In this case is 250. What is the dimensions? Where's the dimension? Here. These are millimeters, 1.64 times 0.99. Meters. And now we need power per area. So it's 250 units watts divided by this area. So we use the calculator. This is 1.64 times 0.99. This is 1.62. 1.62 square meters. And this is 250 divided by 1.62, 154 watts per square meter. Okay, so those are the, so that depends on the panel. I'm selecting this one, but there are more. So even in this catalog, you have more panels. You can select whatever you feel like. Okay. Out of these panels, as long as we have the maximum power at STC and we have information about dimensions, that's fine. So you can use any panel. We can make it even better if we prepare a nice report and we take a picture of this panel. Okay, so the more information you give me, you give your client, the better. So here we have the panel that we have selected with all the information that we need. And then you can copy all these here. Even better, you can do this with different panels. You can have different options and then you can compare the performance. So we can expand this report as much as we want, okay? But at least you have to analyze, you have to let me know what panel you have selected. And then here, this is the data sheet that I need this value. I need the power, the ratio between power and area, okay? Because this is important because this is the value that we're going to use to work with the PV watts. Because now we have option 1 and option 1. The area is 821 square meters. The tilt is 15, and the DC size is 154 watts per square meter times this area. Is 154 times 821, 126 watts. And now we have to turn this into kilowatts. It's 126 kilowatts. Okay, so that would be the DC size. And we need all this information to work with PV watts. We need the tilt and we need the DC size. So let's go to PV watts. We're in ARCH360. Go to the system. Okay, so the tilt is 15. We can assume that this is south, and we are working with the system size. It's 126. 126. Now we go to results, and this is the performance according to PV watts. This is option 1. So the annual is 153, and with Revit it was 179. Yes, this is what I think. Revit is always too optimistic. So I trust, well, I always trust the lowest figure. But, well, I mean, they are like, this is 153, this is 179. We have to make sure that we're analyzing, well, I have not checked the location. So we have to manage and make sure that location it's in Keene, New Hampshire. And now I have to do the same with the other option. In this option, this is option 2. The panel is the same. The area is different. The area now is 460. No, 560. The tilt, it was 39 point something, let's say 40. And the DC size is 100. This is the same. This is 560. Uh, 154 times 560. This is 86. 86 what? 240. which is 86 kilowatts. Now I have to come back to the PV watts, go back here. Now this is 86. The tilt is different now, it's 40. And this is the production now. Select this one. Okay. With Revit it was 131, with PV watts is 112. Okay, if you can see the difference, this is 179, this is 153, so it's 20 something less. With this one is 110 and this is 130. Yeah, so it's like 20,000 kilowatt hours per year less. So that makes me rely on both tools because the difference between this one and this one is the same as the difference between this one and that one. Why is it happening? Well, I don't know. If we have two different softwares, two different tools with two different results, then we need to go to the source. So where does it come from? The PV watts calculator comes from the Department of Energy of the United States government. Can we rely on that? Where does Revit come from? I don't know. Well, we do know it comes from Autodesk. But I don't know, I tend to rely on this official information. And anyway, I would always select the lowest value to be on the safe side. If our client gets more than this, the client will be happy. If he gets less than the more optimistic result, the client will get angry. So we want our client to be happy, or at least this is what they want. But it makes sense. What would be next? Well, next we will have to compare this with the F-chart software. Okay, so we will analyze these two options with the F-chart software. Then we can add the economic analysis, and we can, I don't know, it will be closer to this value, or will it be closer to the Revit value? We will see. But this is the first report. And this is it. We have to select the spaces, then we have to go to the construction details. We have to work with two options, the open rack and the rows. We have to do this with Revit, and we have to do that with PV watts. And then we have to compare the Revit and PV watts output, taking into account that we are using the same PV panel. If you want to go farther, because we have more time, so we can add the passive solar heat gains. Okay, so I'm going to work with the passive solar heat gains, but to do this, because we have done this solar analysis, and usually Revit, if you're working with the solar analysis and you don't stop, at the end, it fails. So I'm going to save it. I would use this for the PV analysis. Now I'm going to close this model. And I'm going to open the original file again. Please. And since I'm analyzing the solar heat gains, well, we are going to analyze this in the spaces in which we have a curtain wall. So I think I'm changing the view. I think that's better because I'm analyzing the solar heat gains. You know, or that if we're using that curtain wall here, the solar heat gains don't work. Why? I don't know, but I have tried many times, and I have read some forums, and yeah, Revit I think is aware that they have an issue with solar analysis and curtain walls, and they are fixing it as far as I understood. But I have found like a way to deceive Revit. We can no, we can select the curtain walls. Make sure that you select the panel. You don't select the, so you select the whole wall. You don't select the mullions or the, I'm going to analyze the grid space and the studio. So this is a northern curtain wall. And now I hide elements in view. Elements, not category. If you hide category, you select all the walls. So I hide this element. And now see what happens with this solar analysis. Probably we should attach this to the floor. Okay, so we have to fix something here. But now we can analyze solar. We are not analyzing solar energy now. We're analyzing the custom. We're using the sun settings, okay? We have to select, now we are not selecting the roof, we are selecting this floor. And it's cumulative insulation. If we are working with thermal, we can select the BTUs, but I don't like the solar analysis, so solar analysis default. So now it doesn't have anything to do with the PV. We're analyzing the amount of solar radiation that enters through these curtain walls. We finish. Cumulative update. Okay, now it works. Okay, so if we hide in view the curtain wall, and now we have information about the passive solar analysis. As it was expected, this is the south elevation. We have a lot of solar heat gains here. And on the north elevation, it doesn't mean that we have zero. Even we have diffuse light. So you see that we are gaining some energy here, even in the north elevation. But the maximum solar heat gains come here. Can we do this on yes, this is from January the 1st to December the 31st. Okay, I can take a picture of this. And now I can work with the passive analysis. So this information is about the yearly here. Okay, but I think when it comes to solar heat gains, it's good comparing the solar heat gains that we have in winter and the solar heat gains that we have in summer. So I would use the yearly analysis and then the seasonal analysis in winter and summer. That will be winter and summer. I have to use the sun settings now. I can work with summer solar study. it goes from June to September, sunrise to sunset, apply, okay. And now make sure that here we have the use the sun settings. Yep. We can use the selection, make sure that we are selecting the same floor. Finish, cumulative, installation. Let's use the BTUs because we have selected BTUs. Sort default analysis and update. Okay, so in summer, this is the outcome in summer. Send it back. And now we need the same thing in winter. We have to go to the sun settings again. Now we have the winter solar study, sunrise to sunset from December. No, what is this? I think something. Okay, so it's from December the 21st until March the 21st, but next year. Okay. Be careful with this solar analysis because sometimes it's okay. So this is from December 2010 until March 2011. I don't know why it's not working. Oh no, this is 12. Maybe Revit is working well, and I'm not used to placing the month at the beginning. So this is December the 21st, and this is March the 21st. Okay, so let's see how it goes. Yeah, so we have from December to March. Okay, and as it was expected in winter, we have a lot of, in this south elevation, we have a lot of heat gains, which is good. There you go. So this is in summer. Well, I think I use BTUs, and kilowatt hours. Okay, you have to fix this. You have to use the same units. But if we compare the summer and the winter heat gains, in winter we have 65. In summer we have only 1,000. So this is 65,000 BTUs, and here we have only 1,000 BTUs. So that works, okay? And that works probably because this overhang is preventing some of the solar radiation from entering here as well. But that's the meaningful analysis. So we have to enhance the solar heat gains in winter, and we have to prevent solar heat gains in summer. This is 1,000, or is it 1 million? No, this is, we're talking about millions. It's 65 millions, and this is 1 million. Yeah, it's not 1,000. Here we have the percentage or the BTU per feet square. This is 42 in summer, and this is 2,600. So that makes sense. Now we have to analyze the heat losses, and we can analyze the heat losses using the tool that we use, the Excel file, with the triple glazing, with the north, with the area that we have in south and we have in the north elevation. And then we can compare the heat gains in winter to the heat losses in winter. Okay, that would be even more. But at least this is something meaningful. So we have this table of contents, we are defining what spaces we are analyzing, we have two options. And I'm sure that they did this because Peter Temple told me that they had analyzed and then they had decided on this. Because they, with using rows, you have fewer panels, because at the end you have to separate the panels, because if you place them too close to each other, you have shadows and the performance is affected by this. Okay, so using this, it's better because first, well, I think it's more appealing. Having this, if you want to go green and you want to claim that you're sustainable, you have to show off. So you have to show this to the rest of the world. With this, you have to know. Believe me, there are panels on the roof. Oh yeah, yeah, I do believe you. But with this, I see that there are actual panels on the roof. With this, yeah. So maybe if I walk to the roof, I can see that there are panels. So that's appealing. And second, would you maximize the area with this? You make sure that none of the panels is casting shadows because they are on this tilted roof. With this, we can always have risk of casting shadows between different rows of the panel. Well, so I would go for this solution, although it's more expensive because you have to add the price for the structure. Here, you don't have any auxiliary structure to place the PV panels. It's very simple. So here, this is probably more expensive. You have to pay more money upfront. But is it worth it? Well, this is what the PV chart will analyze in terms of economic analysis, and then we can have another factor to make a decision. Here we we compare the Revit analysis to the PV watts analysis using an actual panel, because in Revit, that's another thing. We don't know what kind of panel Revit is using. Probably we know, but we haven't done this, so we haven't included the characteristics of a PV panel here. Probably the maximum power at STC we are using in Revit is more than the actual panel that we are using in PV watts. And maybe that's why probably Revit is more optimistic than the PV watt analysis, because we have done this with the actual panel and the actual performance. And this is not great, by the way. Having a 140 watt PV panel, it's not something great. So probably we can maximize the PV production by using a different panel. But anyway, this is the actual value, and this is the actual value of the DC size that we are planning. And finally, we can use Revit to analyze the solar heat gains. The only thing that I don't like, yeah, I can understand that in winter we have much more energy than in summer, so that's fine, that's good. But the problem is that I can't apply here the solar heat gain coefficient, because in Revit, if I show the actual curtain wall, by selecting the curtain wall itself, I can't see what kind of glass we're using. But if I select just a panel, okay, so if I filter and I select only curtain panels and I edit type, now I see what kind of panel I'm using. I'm using the single glazing. So the first thing I have to do is to change this to triple glazing. Okay, one of these low emissivity triple glazing. And here I can control the solar heat gain coefficient. In the south elevation, I would use, well, or I don't know, but I can control the solar heat gain coefficient. It can be from 0.2 to 0.65. Okay, so I can select this. And now the thermal resistance and the heat transfer coefficient, it's 0.2. 0.2 is quite good for glass, so then I can apply. So I would like to have this because if I were analyzing this with using the curtain wall, the actual curtain wall, I'm sure that Revit could take into account the solar heat gain coefficient. But by deleting this, Revit is not taking into account the solar heat gain coefficient. So the total value, yeah, the value that we have here is not the actual value. We can find it out by multiplying this times the solar heat gain coefficient. Okay, we can do that. The actual solar heat gains would be a million 5 BTU times the solar heat gain coefficient. So the solar heat gain coefficient, it was 0.65. 65. Okay, so that would be the actual solar heat gain. And now, if I'm using Revit, if I'm a business user and I'm paying $2,000 a year for using Revit, I don't know. I think that I would expect that they can take that into account. I don't have to do this. But here would be 1.65931 and 0.042. Okay, so that would be the actual solar heat gains, is this number times the solar heat gain coefficient that I have decided. Come on, Revit, you should be able to do it. So this is a call for Revit developers. Please fix this as soon as possible.